The task is that you're going to have to do some modelling on some brackets that I've actually made the model. So all you've got to do is load it up and do the simulations on it, get the results, and kind of do an interpretation on it. Yeah. So here, the first thing that you need to do is go to on the net. If you go to the computer on the network, there's a public drive or W drive. Don't do it now, please. Okay. On there is a higher education folder, and inside that there's a folder with my name on it, and inside that there's a folder called Maths Loading Exercise. It is read only, so you can't. If you load up from there, you can't do anything with it. You need to make a copy of that and put it on your USB drive or somewhere else. Yeah. Then you can use it. Inside that folder, there are 3 parts that the brackets are made up of. What you need is the assemblies. Okay. You've got an assembly with no webs, an assembly that's just got a web on the bottom, and an assembly that's got 2 webs on it. Okay. Well, I'm going to do my demonstration on the basic assembly without any webs. The idea is that you're going to look at all 3, doing similar things and making comparisons between the results that you get. Okay. So the idea is that adding a web on the bottom is theoretically an improvement. Adding a second web, so you've got a web top and bottom, is theoretically another different improvement to that bracket. Yeah? And you're being asked to load it with 15 kilonewtons and do a range of load tests on it. Okay. So first thing I'm going to do is open up assembly with no webs. Solidworks. Open read only. I can save it again after. And rebuild when it says that. Okay. So what we've got is a bracket that can be bolted to a wall with these 4 holes, and then there's a surface here that we're going to put our load on. In SolidWorks, if you click the wheel, you can pan and rotate around the model, yeah, to look at different parts of it. So our load is going to be placed on that surface, yeah, 15 kilonewtons, pointing downwards, and we're going to analyse what that does to this bracket. Yeah. So the first thing you have to do, I'm going to stop after this little bit, because we need to install the add-in that does the simulation. Okay. So to do that, we have to go to this menu up here and say add-ins, and we get this dialog box up. Okay. And we want to tick against SolidWorks simulation. There's 2 places to put a tick. The one on the left-hand side loads up SolidWorks simulation from this section only. When I turn SolidWorks off, back on again, it won't come up again. If you're a regular user, which you're not necessarily going to be, you might tick Startup. It would then always load on Startup. I don't want you to do that, because 1, if you're not using it, it takes up a lot of memory on the computer. 2, other students plan around with simulation instead of doing what they're supposed to be doing. It's not the idea any other tutors might want. So please tick the left-hand side. When you've done that and clicked OK, you'll get an acceptance dialog box up, and you've now got another tab here called Simulation. Yeah. So if everybody could get to that stage, all right, as quickly as you possibly can, I'd appreciate it. Yeah, I'll just record it. If you lose your model, you can't find it or stall, double click the wheel, I'll always come back to fit the page. Yep. So what you're going to be doing is you're going to be doing simulations on this bracket and similar ones on the bracket with one web and with a bottom web and with two webs. Okay, so first thing we need to do is set up a study. So if you go to this drop-down box, don't pick Study Advisor. Again, it keeps interrupting you with what do you want to do. It's much easier to just follow the method that I'm going to show you. So, new study. Okay, you're able to give it a meaningful name if you want to. Different studies come up in tabs down the bottom. Okay, you're going to be doing a static, so we leave that as default. One thing about Solidworks, I find that seems to know what you want to do most times, and the most obvious thing that you might want to be doing, and it's already got it set up that way. Yeah. So static, you're doing okay. When you're happy with that, green tick, done. Okay. So then what we've got is we've got some extended, what's called a study tree down here of different things that we need to set up before we can do this evaluation. The first thing we need to do is fix something, so that's static. So we need to do a fixture. What we're going to do is make this back plate fixed in space so it doesn't move in any of the three directions. So we right click fixtures and say we want some fixed geometry. And that's giving you an example of what we're doing here. We're going to fix one surface and let every other surface do what it wants to under load. So it's highlighting this box here and asking for the faces, the edges of what you want to fix. So we tick that, and that face comes up in there. And if you look closely, you've got a green arrow in all three directions. So you're fixing it in space. It can't move anywhere. It is possible under advanced to take one or more of those directions off and let it move in two directions but not the third, or just move in one direction and not the other two. Okay, what we want is we want to fix it solid, so we just do that and tick. So what we're saying now is that back plate is fixed in space and ain't going to move. Right? Second thing we need to do is apply our external load. So we right click load, and we're just going to apply a simple force. Again, straight into the right box being highlighted. We could, if we wanted to, apply a torque. We're not going to do that. So the right option is up. We've been asked to select the face we want to apply the force to, which is this top one here. Okay, you should get arrows pointing downwards. If you don't, you can reverse the direction by ticking that box. Yep. And then the last thing to do there is put the load in that you want to apply. I'm going to apply 13,000 newtons rather than exactly what you're going to do. Yeah, and again, tick. So those purpley arrows are saying we're applying 13,000 newtons of force onto that surface. Yeah. Then what we need to do is we need to do what's called the mesh. The mesh is the way the maths is broken down to be able to work out the stress and the strain over the whole volume of that particular object. And I like triangular solids. It breaks it up into. You'll see what I mean in a minute. But what you need to do is right click on mesh and say you want to create the mesh. You're able to adjust to from a coarse mesh to a middle to a fine. The idea being there's a balance between accuracy and processing time. So for your analysis, I'm not expecting you to do anything other than leave it the default in the middle. If we make it coarser, we don't get such accurate results, but would take less time to process, which is not an issue on this particular analysis, but it could be on something more complex. Okay. Also, you go fine. Yes, you get more accurate results, but it takes much longer to process. It's got more calculations to do. So there's the balance there. And when you get more complicated with this, it's possible to have a coarse mesh in areas where it don't matter so much, and a really fine mesh where there's areas where you need more accuracy. So again, you can refine it even more. All right. All we want to do is keep it in the middle, so we just tick. Takes a second or two to set up the mesh. Look at that. And you can see now that it's actually split the bodies into little, I don't know, what's the word for a triangular shape solid? Trihedron or something like that? I don't know. Anyway, that's what split up into. Yeah. So it'll do its calculations on each one of them and bring them all together into an overall result. Yeah. So if you can get that far, please, and then again, let me know when everyone's ready. Right. Once you've set up your load and fixture and meshed your work, okay, then you're ready to run the simulation, and you'll get some basic results up, but we're going to add to those results and look at some different stuff as well. So if you click on run, wait, and it goes through process of solving the problem. Yep, haven't done that. You then got some, usually, some results. That's not quite finished yet. Yeah, results. So once you've run that, you've then got 3 default results, which is a stress plot, a displacement, and a strain. If we look at this stress plot, you've got a scale of colours, between blue being low, the lowest, yeah, and as it go up to red being the highest. The little red arrow is the yield stress of the material. So from mechanical things done earlier, yield stress is that point where that's been stressed, that's been stretched, and it ain't going to spring back, basically. It's been plastically deformed if you go beyond the yield stress. So looking at the diagram, an area in here of very high stress that would be an issue for that pressure. Yeah. If we click on the displacement plot, it gives you, in the red part has displaced the most, 2.03 times 10 to the 0, 2.03 millimeters, whereas red. 2 blue being next to it. Okay, and what the software does graphically is it exaggerates that movement so you can see the kind of shape and direction of it. Because that actually looks like it's moved more than 2 or 3 millimeters. There's a tendency to exaggerate it so that you can see that there's movement there. Okay, so there's a little movement here, and it's what you would expect, the biggest amount of displacement on the end. Yeah. Strain again, there's a colour diagram showing where the different areas of strain are. From blue, not very much, so that's times 10 to the -8, up to red here. And if my memory serves me rightly, strain is a ratio, it hasn't got any units. Yeah. What we want to do though, we want to have a look at one more analysis that I want you to have a look at, and that is factor of safety. So, if we right click results, there's two different factor of safety plots you can do. You can look at both of them. Define a factor of safety plot. This is a dialog box that's got 3 tabs to it, and the only one we're really interested in is the last one. So we leave everything default on the first one, leave the multiplication factor to 1. What you can do is you can do a factor of safety distribution, which is what I'm going to do now. You can also ask it to show you the areas that are outside a particular factor of safety. Yeah. So first of all, we're going to look at distribution. So we tick it, and that's showing me the red areas. Factor of safety is only 0.7, and even 1, let alone higher. And any blue areas, factor of safety of 84,837. Okay. To me, that's not quite as interesting as doing a factor of safety to another factor of safety plot. And this is what you're asked to do in your assignment, is do areas below factor of safety of 5. Yeah. Tick. That is then simply blue for within a factor of safety of 5, red not within a factor of safety of 5. So what we're saying is we want this to hold 15 kilonewtons, but we want a factor of safety of 5 times that, which in a way is a bit excessive. Okay, you might go on some things where you work, you might have a factor of safety of 1.5 or a factor of safety of 2. I've never worked in this area, so I don't know what industry standards are. But there will be, for things like lift and eyes, there'll be a factor of safety. Yeah. So you're looking for it to be, you know, if you're gonna make a crane to lift 2 ton, you actually want it to be able to lift, for example, 3 ton or 4 ton. So you've got a factor of safety. Yeah. So that's showing me that this bracket is outside a factor of safety of 5 for a 13 kilonewton load. Yeah. Your assignment is then asking you, if it doesn't pass that test, to investigate what load you could apply. So the maximum you could apply and still and come within that factor of safety of 5. Now, my recommendation for you to find that is, 1, I don't want it to the nearest newton. The nearest 500 newtons will be perfectly fine. And use the halfway in between method. So, add half the load. Is that okay? If it is, go up halfway between that and 15,000. If it isn't, go halfway between the halfway mark and 0. And eventually, you'll find to the nearest 500 newtons roughly what load you could put on that and apply with a factor of safety of 5. Okay? Sorry? Well, what I'm not looking for loads of screen snips of these results. Guys, can you just listen to me for a minute? Because what I don't want is reports with hundreds of bloody screen clips in them of you trying to find what load will answer a factor of safety of 5. Yes, screen clips of each result to give an example of how this software works. A results table that compares the maximum load on this bracket to the maximum load you could apply to the one with a web on the bottom to a maximum load you could apply to the one with 2 webs. the stress of each one compared. It's no good comparing the stress with the strain. They're not valid. You want the stress of each bracket compared, the strain of each bracket compared, and so on. Factor of safety compared. So many times I get table of results for each bracket. Well, look what you're looking for. There's a table of all the results comparing each of these things across all three brackets. Yeah, and you'll notice there's some interesting changes that happen, and you might find it interesting as to which bracket you think is active and which one will take the most load. Okay, so that's what I'm requiring you to do for your assignment, is to carry out those simulations across those three brackets and do a comparison and say a little bit what you think about that process mathematically, because it's doing some quite complex calculations that you wouldn't want to do on a piece of paper and with pen. All right, everybody happy? Yeah. Yeah. No, when you do compare to a factor of safety of X, in this case 5, it only shows you blue areas that are okay to that factor of safety, that would take 5 times the load. Red is areas that wouldn't take that to a factor of safety of 5. Yeah, but on this plot it won't show you any green. This plot will only show you the extremes. Good, bad. Yeah? And that's why I think that's better than, for what we want, that's better than the factor of safety distribution, because it's giving you the answer to a particular factor of safety. All right? So as far as I'm concerned, I'm done there. Of course, I'll come around and help if you're having trouble. But the rest of the time for this module is down for you to get this software work done and work on that assignment. All right? That's in 30th of January. So in the exam weeks, which you haven't got any exams, if I remember rightly, your part-timers haven't. You guys, you and Ben have. You got exams, but this room is booked for this session during that time. So if you can be here and you want to do any more simulation, you can work in this room. There's PLC assignment. Oh, what now? You use your time how you want to use it, Cal. You're not here at all next week. PLC software I don't think is on these machines now.